Hello, students! Today, we're going to understand a very fundamental concept in organic chemistry. We'll be exploring the nature of the CX bond, that is, the bond between a carbon atom and a halogen atom. Believe me, this single idea is the key that will unlock why haloalkanes react in the specific way that they do.
So let's start with something you might have done in the lab. You take one bromobutane, you mix it with some aqueous potassium hydroxide, and you see a reaction happen. But have you ever stopped to ask why? I mean, why does the OH group come and replace the bromine? Why doesn't the bromine just stay where it is? Why does the substitution reaction happen in the first place?
Well, the answer to all of these questions, it lies in understanding the hidden nature of the bond itself, that CX bond. See, it's not just a simple line that we draw in our notebooks. It has a very specific character, a secret, if you will, that we need to uncover.
At the simplest level, here is the crucial point you must remember. The halogen atom is much more electronegative than the carbon atom it's bonded to. Now, what does electronegativity mean? It's simply the power of an atom to pull the shared pair of electrons in a bond towards itself. And when it comes to this pulling power, halogens are very strong.
A really great way to picture this is to imagine the halogen atom as a powerful magnetic vacuum cleaner. And the shared electrons in that bond, they're like tiny dust particles. So what's going to happen? Obviously, the vacuum cleaner will pull all that dust towards itself. In the exact same way, the halogen pulls the electron cloud of the bond strongly towards itself.
Now, this slide gives us the proper exam-safe definition. Let's read it. The CX bond is a polar covalent bond. Now, this word, polar, is the absolute key. Because the halogen pulls those electrons, the bond becomes polarized. It gets two poles, like a magnet. One end becomes slightly negative, and the other becomes slightly positive. And this is exactly what makes that carbon atom vulnerable to an attack.
Let's build on this idea using a very simple analogy. Honestly, the best way to remember this entire concept is to think of it as a game of tug-of-war.
Look at this comparison. It makes everything so clear. In a tug-of-war, you have two people pulling a rope, right? In the CX bond, you have carbon and a halogen sharing electrons. Now in the game, one person is much stronger. In our bond, the halogen is much more electronegative. So what happens? The rope moves toward the stronger side. In the bond, the electron density is pulled toward the halogen. And the most important part, what happens to the weaker person? They get pulled forward. They become unbalanced. In the same way, our carbon atom becomes electron deficient. We say it gets a partial positive charge, which we show with this symbol delta plus. So you might be thinking, why did chemists even come up with this idea of bond polarity? Well, it was to solve a very real problem. It perfectly explains why haloalkanes are so reactive while simple alkanes are quite unreactive. And even more importantly, it answers the question, why does an incoming attacker, what we call a nucleophile, why does it always attack the carbon atom and not the halogen atom? This concept gives us the answer.
Okay, now let's build a very clear mental picture, step by step, of what this polarity actually looks like at the molecular level.
So, we always start with the basic picture we draw on paper. A carbon atom, a single line representing the covalent bond, and a halogen atom, which we can just call X. Simple enough, isn't it?
But in reality, that sharing is not equal at all. Because of that powerful halogen vacuum cleaner we talked about, the cloud of shared electrons gets pulled out of shape. It's no longer symmetrical. The electron cloud becomes thick and dense near the halogen, and it becomes thin and sparse around the carbon.
And this lopsided electron cloud is exactly what creates the polarity. We show this by using partial charges. The carbon, because it has lost some of its electron cloud, becomes partially positive. We write this as delta plus. And the halogen, which has gained that extra electron density, becomes partially negative, or delta minus. So now our bond looks like this: C delta plus connected to X delta minus.
And now, everything comes together. Imagine a nucleophile is approaching this bond. Now, by definition, a nucleophile is rich in electrons. It carries a negative charge. So where is it going to go? It will be repelled by the partially negative halogen, right? But it will be very strongly attracted to the electron-poor, partially positive carbon atom. That carbon becomes the target, the site of the attack. And this, my students, is the secret to all nucleophilic substitution reactions. So you see, this simple idea of a polar bond is not just some abstract theory for exams. It has very important, very real consequences, both in our school laboratory and in developing modern medicines that save lives.
Let's go back to the question we started with. When you mix 1-bromobutane and potassium hydroxide, what you see is a reaction that forms butanol. But now you know why it happens. The CBr bond is polar. The carbon is delta plus. The hydroxide ion, the OH-, is a nucleophile. It's attracted to this partially positive carbon. So it attacks the carbon and the bromide ion gets kicked out. It is the polarity of the bond that makes this whole reaction possible.
And this predictable reactivity is an incredibly powerful tool in technology. For example, in drug synthesis, chemists use haloalkanes as building blocks all the time. They know for sure that the carbon atom is a reliable target for attack. So by using the CX bond's polarity, they can precisely attach other functional groups and build very complex drug molecules. This very principle is essential for making so many modern medicines, including important antiretroviral drugs used to fight HIV.
Okay, so let's quickly recap the most important points from our discussion. If you can just remember these few things, you have fully understood this topic.
So what are the 3 key points to take away? First, the core idea. The CX bond is polar because the halogen is more electronegative and pulls the electrons. Simple. Second, the key analogy. Just think of it as an electron tug of war, where the poor carbon loses and becomes partially positive. And third, the all-important consequence. This partially positive carbon becomes the target for attack by any incoming nucleophile.
So, my final advice to you is this. Whenever you see a CX bond, just remember the tug of war. If you can remember that, you will always be able to figure out the polarity and predict exactly where the nucleophile will attack. Just remember that one core idea, that one mental picture of the tug of war, and one good example. And I promise you, this entire topic will feel much, much lighter and easier for you in your exam.